Hello, everyone. So this is the first class of this semester. We're gonna sort of continue from last semester, uh, but the focus is different now. Last semester we studied different topics, including extremal graph theory, extremal set theory, and a gentle introduction on the regularity lemma. This semester, the course will be mostly on different methods that are very useful in extremal combinatorics. So the first method we're going to study is the entropy method. So entropy is a notion from information theory, notion of entropy. Um, Before stating its formal definition, I would like to say roughly what it means. So entropy is defined for a random variable. So the setup is like this. We have a random variable. Let's say x. And in the future, I will just use r dot b to indicate the shorthand for random variable. So we have a random variable x, and its entropy, the entropy of x denoted by h of x it's a function that assigns a random variable some non-negative value. So it assigns, this is a non-negative real value, which measures sort of the amount of information. You can think of the amount of information the random variable carries, or sometimes it's helpful to think of amount of surprise or the amount of randomness. So let me illustrate through a very, very simple example what this means. So the simple example would be, let me first state its formal definition. So if we have a random variable x defined taking value or defined on some discrete set of elements A, let me use this shorthand p sub x to indicate the probability that the random variable x takes value little x in A. Okay. Then the entropy is defined as h of x equals to, we sum over the probability that x takes value little x times log of 1 over px, where we take all possible values in A. Here, throughout this first part of the course, when we talk about entropy, since it's coming from information theory, all the log will be on based on 2. So the log is base 2 log, and the convention is 0 log 0 is 0. It's just a convention. Okay. So let's see through this example what this intuitive meaning of entropy means. So this is clearly, we have the probability, which is a real number, non-negative. And then this is just this sum of some real number. This is a non-negative real number. And the more random x is, the more information surprise you will get from the entropy. So let's consider a coin flip. Consider a coin flip. We have heads and tail, right? The outcome of the coin. If we have a coin that we know both of its sides are head, so with 100% probability, probability 1, you will get head. With probability 0, we will get tail 0. We will get tail. Then what's the entropy of this random variable? It's not really random, this random variable. It's quite deterministic. So the information that it carries is very little, because even before this random experiment takes place, we know the outcome already. So let's compute what is the entropy here. So for this, in this case, h of x, so if this is x, h of x equals to what? Equals to, we have sum of two outcomes. So this is A. The set A is head or tail. We have the probability 1. It takes head plus probability 0. Maybe I should write this. Log 1 over 0. And log 1 is 0. This is 0, which makes sense because this is deterministic. It carries no information, no surprise. Okay. Now let's look at a slightly more reasonable coin flip. Let's assume our coin is a fair coin with probability 1/2 to have tail and 1/2 to have head. It's a normal coin flip. What is then the entropy of it? Well, h of y, this random variable, we have probability 1/2. You have log 1 over 1/2, and which is log 2, 1, plus tail. Easy to compute. This is 1. Each summon is 1/2. And later we will see that if you adjust this probability, we only have two outcomes. So the probability is always A plus B equal to 1. The maximum entropy we will see is the fair coin flip, which is 1. So I'll leave it as a simple thing to check. This is a very simple exercise to check that if we have a random variable z that takes value head with probability 1/3 and tail with probability 2/3, then h of z is somewhere between 0 and 1, where 0 is no surprise and 1 is the maximum surprise because it's fair coins. Every side is equally possible. Whereas in the tilted case, if you are more likely to take tail, then the amount of the surprise is less because we know more likely the outcome is tail. All right. So So here, let me state two properties without proving without proving it, and then we will see a quick application of entropy to appreciate these methods before we diving into the details. So let me state with two properties. Lemma 1. This lemma 1 says the following. If we have a random variable, x, which is uniformly distributed over a set A. So this is the notation, meaning that x is uniformly distributed over A. Meaning x equals to A with probability 1 over A for any A in A. All right? So we have a random variable uniformly distributed over a set. Then its entropy the entropy of x equals to base 2 log of the size of the set A. So this is the first lemma. Let's take it for granted. We have a second lemma, lemma 2. Okay. So maybe one quick comment about the first lemma. The first lemma already indicates sort of why the entropy is useful, because suppose in many discrete problems in combinatorics, what we want to do is we have a discrete set of objects where it could be A, it's our A. We want to give an upper and lower bound its cardinality. We want to get an estimate on how large is the set A. Then we know that the entropy, when we uniformly sample an object from A, the entropy of this random variable then is directly linked to the cardinality of A. If we have a way of getting bounds on the entropy of this random variable, then we will have a way of bounding the cardinality of A. Okay. So here through this lemma, bounding h of x gives us bounds on A. The second lemma, which is more intuitive than the first one, it's called, before the second lemma, maybe I should mention the joint entropy first. Suppose now we have two random variables, x defined on A. We have a random variable y defined on another set B. Then their joint entropy, again, I will write PAB to be the probability that x takes value little a and y takes value little b for any A in A and B in B. All right? Then the joint entropy is h of x, y equals to the sum over all A and B, such that the summand is PAB log 1 over PAB. It's very similar. We can again, think of this as the joint information that X and Y together carries. X and Y carry, it should be plural. The second information is that it's called subadditivity. What subadditivity says is that the joint information that two random variable carries is never more than the sum of amount of individual informations that these two random variable carries. So h of x1, xn, let's say we have n random variable now, you can define their joint information entropy in the same way, is at most the sum from 1 to n, the entropy of each individual one of them. This sort of also makes sense if you think about it, because if, roughly speaking, if these random variables, they have nothing to do with each other, they are independent, then knowing one information, and then you see the information that x2 carries, it's a new set of information. Then equality holds, right? It equals to the sum of them. But sometimes knowing x1, x2 give you already some information about x3. Then revealing x3, you only gain maybe a little bit more. So their joint information is never more than the total sum of the information each random variable carries. We will prove this later, but let's remember this intuitive meaning, right? So without proving this two lemma, we can already see a quick application. So this is a simple application to estimate the volume of a Hamming ball. Okay. A quick application. All right. So let's see this definition of a function called binary. Well, to not get confused, this is just a definition of a deterministic function. It's called, happens to call also entropy. So the binary entropy function, which is a deterministic function, h, is defined as hp equals to p again log base 2 plus 1 minus p log 1 over 1 minus p. Now, if you recall our definition of the entropy, if you recall this definition, you will notice that if we define x as a coin flip where the head is probability p and the tail is probability 1 minus p, and if you plug in this definition, that's precisely little h of p. So what this means is that the binary entropy function is defined so that the value of hp is precisely the entropy of a Bernoulli random variable with probability p. So note that little hp is the entropy of a Bernoulli random variable with probability P. Okay. We can estimate binomial coefficients using this binary entropy function. So why is this useful? Using Stirling's formula, we can write, so by Stirling, n factorial asymptotically when n goes to infinity is roughly the square root of 2 pi n times n over e to the e as n goes to infinity. This is it's not a hard estimate. And simple calculation shows that also n choose Pn, if you take P between 0 and 1, this is roughly, if using the entropy function, 2 to the little hp times n over some lower order term, which let me write it out, 2 pi n p 1 minus p. Now, if we should think of n is large, tends to infinity, and p is fixed. In this case, let's look at this estimate. This binomial coefficient is roughly 2 to the hpn. This is a way of estimating it because this is exponential in n, whereas the denominator is just a polynomial in n. It's a lower order term. We should think of it, this is roughly this guy, all right? Now, to define the Hamming ball, we have to define the Hamming distance. The Hamming distance is defined as a metric to measure the distance between two binary vectors. So if we have two vectors, the Hamming distance between two vectors is the number of coordinates where they differ. Okay. Here's a very simple example. If you have 0, 0, 1, 0, 1, 0, then where do they differ? So these two, the Hamming distance is equal to 3, right? In these two cases, in this case. Now, the Hamming ball around, so if you have we fix a binary vector of length n, the Hamming ball of radius r around v is just the set of all vectors with Hamming distance and most r from v. It's not hard to see by symmetry that no matter where we fix this binary vector v, the size of a Hamming ball with a given radius is always the same. So we may as well fix v to be the all-zero vector. If we fix v to be the all-zero vector, the Hamming ball of radius r around v will be all the vectors with at most r1s. Okay? In other words, the size of this size equals to precisely the sum of n choose I at most r, because we're going to choose at most r position to flip 0 to 1. Okay. All right. So as we've seen, we can use this entropy function to give a fairly good estimate on the size of a Hamming ball. Okay, because for every binomial coefficient, if we let's think of the radius to be linear in n, say, then for every binomial coefficient, we can get an asymptotic formula using this binary entropy function. Now let's try to use the entropy of a random variable to give an estimate of the size of this Hamming ball. Okay. This is theorem. Let P to be between 0 and 1/2. Then for all n, we have the Hamming ball of radius, let's say Pn, n choose I, is at most 2 to the hp times n. First of all, before I prove this, let's just try to appreciate this upper bound from this entropy method. This upper bound is fairly tight. You see, if we don't consider the whole sum, let's just consider the very last term, which is n choose m pn, right? The very last term is n choose pn. So this guy is at least n choose pn. But what is n choose pn? N choose pn is this term, right? As I said, this is the leading term, exponential in n, whereas this is polynomial in n, a lower order term. So we can almost determine at least the main term of this size of this Hamming ball, right? How do we prove this? I already gave you the hint. Let's recall. Use the very limited amount of information we have introduced so far. How do we get this upper bound? Recall, we have these two lemma. One is that if we uniformly at random sample elements from a set, then the entropy of this random variable is linked to the cardinality of this set. In particular, equals to the log of the size of this set. So if we want to get the upper bound on the size of this set, what we can do is we can uniform random sample element from this set and get the upper bound on the entropy. Second of all, we know this sub-additivity. The joint information then of a collection of random variables carries is at most the sum of information of each individual random variable. All right. That already give us the hint where to go. The set A here we want to estimate is basically this Hamming ball of radius r. Right? So what we can do is we can uniform at random sample an element from a Hamming ball of radius r. And then we try to get the upper bound on the entropy. So here's the proof. Let A be the set of all subsets of size and most Pn in n, the first n integers. Remember that there's a natural correspondence between 0, 1 vector of length n and the subset n, right? If we think of subset of n, and consider its characteristic vector. So here, the size, this set A is nothing but the Hamming ball of radius Pn around all zero vector. Now, if that's uniform random sample an element from A. So this is a random variable, X, uniform random sample from A. We know by lemma 1, it shows h of x equals to log of size A. So our goal now is to prove this is at most little hp of n. If we can prove this is log base 2, we have the bound we want up here. This is size of A, right? So here's our goal. All right. To use subadditivity, we should think of this random variable x as a random vector. So think of x as a random vector, x1, x2 to xn, where xi is the indicator function that the element I lies in the set X. Okay. What does subadditivity says? Lemma 2, subadditivity says that h of x, which is the same as this collection of indicator functions, is at most the sum of each xi. I goes from 1 to n. By symmetry, each element I for different I, its probability, they have the same distribution. Okay. How does xi looks like? Um, since x is uniformly a random chosen, its weight is never more than p, n. So that means every element I has probability at most p to lie in X. So note that h of xi equals to little alpha I, where alpha I equals to the probability that I lies in X. Okay. By definition of this binary entropy function. But what do we know about this probability? This probability is at most p. As X has size at most Pn. Okay. So it's easy to check that this binary entropy function is increasing in the range 0 to 1/2. And our P is chosen in this range 0 to 1/2. So this is maximized when we take alpha I to be the maximum, which is little p. So this implies that each individual information is at most little hp, which finishes the proof for all I. So we have each summon is at most hp. We have n of them. Okay. Any question? Here's an exercise to show that using this estimate on the Hamming ball, using this theorem, we can prove a weaker version of Chernow's inequality. So here's the weaker version. I would say it's corollary. So you have X, which is a binomial random variable, n trials, each trial with probability 1/2, with standard deviation sigma equals to square root n over 2. Then for any C, the probability that X deviates away from its expectation n/2 by more than C times the standard deviation is at most 2 to the negative C squared over 2 plus 1. So you can try to derive it yourself from this estimate. Now let's come back to the entropy. Here is just a quick application to see two very simple lemma, where one lemma is that when you uniform random sample a random variable, the cardinality of this set is linked to the entropy by definition. The second one is the subadditivity, which is also intuitive. Now, what I want to do is let's try to forget about this formula, this definition of entropy, and let's try to study entropy from an abstract point of view using axioms, the axiomatic approach, which I think it's easier because all we need to do is to remember a set of axioms, and then we can derive all these properties using this set of axioms. The advantage of this approach is that we don't need to do this tedious calculation using this definition. We can just prove things in an abstract way using this set of axioms. But before that, let me define one more variation of entropy, which is called conditional entropy. Again, the setup is that we have random variables x and y, where x is defined on A, and you have random variable y defined on some set B. Then the conditional entropy of y given x is defined as, it's written like this. Conditional entropy of x of y given x is the sum over all possible values that x can take, PA, times the entropy of y given x equals to A. All right? So this is a random variable. Remember, this itself is a random variable, a conditional random variable. Given x equal to A, how y behaves. And it's a random variable. You can measure its entropy. After you measure the entropy, you take the weighted sum for each little a. And this weighted sum is basically the expectation, right? When you take little a. So another way to write this is the expectation of a in A the entropy of y given x equals to a. All right. What we can think of this, again, intuitively, is that this is the information that we get from y after we already know everything about x. So intuitively, we can think of it as the additional information we get from y after we already know everything about x, after knowing x. Okay. With the definition of entropy, joint entropy, and conditional entropy defined, now we can switch gear and study entropy from axiomatic point of view. So there are 6 axioms, but what really matters is 5 of them. So let's see. This is Shannon, Hinchin, entropy axioms. There are 6 of them. The first one, it's called invariance. So invariance says the entropy of a random variable x depends solely on the distribution of x. The entropy of x depends solely on the distribution of x, the probability distribution of x. So what does this mean? That is, if you have 2 random variables, they have the same distribution, then they have the same entropy. So if you have x on A, y on B, random variable, and if you have a bijection phi from A to B, such that these two, you can biject them. So F equals to probability of y of phi A. What does this mean? This means these x and y, they have the same distribution. Then, and their entropy are the same. Then hx equals to hy. All right. Sometimes we also write, okay, like this. Now, what this implies is that, so this is the first implication. If they have the same distribution, they have the same entropy. Another thing, consequence of invariance is that if we have y, this is the first one, and if we have another, if we can write y as a function of x, some deterministic function, then their joint information entropy equals to entropy of x. How to explain this? This is because This is because if we know X already, then since f is a deterministic function, we know everything about y. So the joint information x and y carries, if you already know x, y does not contribute anything. It's the same information as just x itself. The second property, called maximality, this one looks a little bit familiar with lemma 1. It's the second axiom. Maximality. It says that if we have x taking value in A, from a set A, then the entropy of x is maximized when x is uniformly distributed over A. If you have any other distribution over A, the entropy can only be smaller. We have seen this in this toy example of coin flip. If the coin flip is uniform, one half to have heads or tail, the entropy is maximized, which is 1. But if it's tilted, it's any other combination, not one half, the entropy can only be smaller. This is maximality, which is also intuitive. Because when you uniform the random distributed over a set, this is the most random you can get. Anything could happen with equal probability. So the amount of surprise we will get, we cannot predict it, right? The third one, called extensibility. Extensibility is simple. It just means that if x is defined, if we have random variable x on A and y on B, where B it's a superset of A on the larger set, and if the probability that x equals to A equals to probability of y equals to A for all A in A, what does this imply? This in particular implies that the probability that y equals to B is 0 for any B in B minus A, right? So in this case, then they have, again, the same entropy. Then h of x equals to h of y. In fact, if you recall the definition of invariance, extensibility is just a consequence of the first invariance axiom. Let's just write it separately so easier to use. Simply because we can define this bijection, but we sort of think of B minus A elements as dummies. They don't play any role, right? It's basically the same. The fourth axiom, additivity. This is an important one. Additivity says the join information to random variable carries equals to, first of all, the information that X carries, that offers, plus the additional information that Y gives us after knowing X. Right? Once again, this is the total information they give. This is information that X alone gives you. Now, we already know X. We ask, what's the additional amount of information that Y gives us? Together, that's the joint information X and Y offers. Continuity. Continuity says the entropy of X depends continuously on this atom probability. So these are the 5 important axioms. We're going to list one more, which is just so that it will match to our original definition. It's called normalization. Normalization says if X is a uniform random variable over 2 values, then its entropy equals to 1. If X is uniformly random over some set A of size 2, then h of X value equals to 1. This should look not so strange because recall the coin flip. You have heads or tail, and we compute this entropy using this original formula that the entropy is 1. Here, we just list this as an axiom, right? We will later see that this 6 axiom will determine this entropy function. We will see that all these 6 axioms together shows that this definition is the unique function that satisfies all 6 axioms. Later we'll show. All right. So after lay down these axioms, we can start proving basic properties of entropy. So let's recall this, quickly go through these axioms one more time. Invariance basically says if you have 2 random variables have with the same distribution, their entropy is the same. Basically, you have 2 same random variables. The amount of information they carry should be the same. A consequence of this is that if a random variable can be determined by another one, by a deterministic function, then their joint information is the same as just knowing just the original random variable. Maximality says if you have a random variable distributed over a set, its entropy is maximized when it's uniformly distributed. Extensibility is nothing but if you add some dummies, it doesn't change the entropy. Right? Additivity says the joint information equals to information of one of them plus the additional information you get from the other one. Continuity is just some technical one. Normalization says, okay, this is a way of normalize the entropy. If you uniformly distribute it over a set of size 2, entropy is 1. The first basic property is called independence. If we have X and Y, they are independent random variable. they have nothing to do with each other, then the conditional entropy of y given x is the same as the entropy of y. Okay. Why is this intuitively true? Since x and y, they are independent, knowing x does not give us anything about y. So the information we get from y is just the same as its own, right? And another thing is, and the joint information of x and y equals to their sum. This is also intuitive. Well, since x and y are independent, their joint information just the same as the individual information you get from them and take their sum. As a consequence of this is that, in particular, or in general, if xi are independent copies of x, then the joint information of n copies of IID copy of x equals to n times entropy of x. All these statements looks very intuitive. Now let's prove it, not through the definition of this explicit definition that we've seen at the first place, but through the set of axioms we just introduced. So for the first one, we do have to use the definition of the conditional entropy. Let's recall, conditional entropy definition is the sum of the probability that x equals to a and the entropy of y given that x equals to a. This is the definition. Okay. But what is this guy? This guy equals to h of y. Since x and y, they are independent. It has nothing to do with how x behave. So we have this equals to the sum of px. Let me write this as px times h of y. Now, h of y is just some real number that gets assigned to y. The entropy of y is a fixed number. So we can, this is a scalar, we take it out. What's the sum of px? It just equals to 1. The second one is the consequence of the first one. For the second one, remember additivity. So here, actually, what we use is we use x, y, they are independent, and also we use invariance axiom. Because we basically map every instance of yx. This is a bijection to y for every y in B, right? Where capital Y is defined, if you think about it. The second one is by additivity. Additivity, the axiom, remember what additivity says. The join information equals to the information you get from X plus the information you get from Y additionally on top of X. What we know is that since X, Y are independent by the first part, this equals to H of Y. And that's it. This one, I will not write the proof. It's very simple also. Since they are independent, this equals to the sum of each one of them. And each one of them, by invariance, they have the same distribution. So they have the same entropy as X. The last one follows from invariance, basically. The second property is that we've also seen it in this toy example. If we flip this coin, we know 100% it lays on head and 0% it lays on tail. If the outcome is deterministic, then the entropy is 0. The amount of information it carries is 0. We're going to prove it, formally prove it. This lemma says if X is a random variable, taking only one value, so it's always head, then the entropy of X equals to 0. How do we prove this? Using axioms. We consider two IID copy of X. Let X1, X2 be two independent copies of X. Okay, let's consider its joint entropy. So the joint entropy on one hand, X1, X2, by invariance, since X only takes a single value, we can do a bijection map just anything, right? X by invariance, and that X takes only one value, you can find the bijection. So this is the same as the entropy of X, bijection between X1 and X2 to X. There's only one outcome, right? You can do this. On the other hand, they are independent random variables, X1 and X2. Independence means we can use the previous lemma that then they equals to the sum of entropy of each one of them when they are independent. And X1, X2, they are IID copy of X by invariance. Each one of them by the previous one is 2 times H of X, right? So 2 times H of X equals to H of X. These two are the same. So H of X is 0. This property is basically saying that when the outcome of X it's a certainty, then there's no information, no randomness this random variable carry. The The third property, you can think of as a monotonicity. The first monotonicity, it says the following. If you have two sets, A and B, where A is less than equal to B, let's say, and if we have random variables, X defined on A and Y takes value on B, then I do really mean uniformly distributed. We have X uniformly distributed over set A and Y uniformly distributed over set B. Then the uniform distributed one over the larger set has larger entropy. Where with equality holds, when if and only if A equals to B. Okay. The first thing to notice is that by invariance, we may assume A is a subset of B. You can just build a bijection between A and a subset of B of cardinality the same as A. So we may assume A is a subset of B by invariance. So to prove this, first, by invariance axiom, we may assume A is a subset of B. Okay. Now, if you assume A is a subset of B, we can then think of X now as a random variable defined on B. We can think of X defined on B as follows. Well, the probability of X equals to A equals to 1 over A for every A in A, and the probability of X equals to B equals to 0 for any in B minus A. Right? This is what it means. X is uniformly distributed on A. We think of it defined on B just so that in this set it takes value 0. So now we have two random variables. They are defined over the same set B. But what do we know by maximality? If you have two random variables defined over the same set, the one that's uniformly distributed over that set has larger entropy. That's maximality. Let's recall maximality, right? If we have random variable taking over a set, entropy is maximized when it's uniformly distributed. Now we have both X and Y defined taking values in B, and Y is uniformly distributed over B, where X is not. Okay? Y is uniformly distributed over B. X is distributed like this, not uniformly distributed. So by maximality, h of X is at most h of Y. Here, we use extensibility technically to think of Y as a random variable on B. Now, what we need to prove is this if and only if case. In other words, we need to prove if A is strictly less than B, then the entropy of X is strictly less than entropy of Y. We are left to show if A is strictly less than B, then entropy of X is strictly less than entropy of Y. Well, this is true if A is of size 1. Why? If A is of size 1, then by the previous lemma, X uniformly distributed over a set of size 1. It takes one value, entropy is 0, right? And Y is what? Y is distributed over some sets of size at least 2, because B is strictly greater than A. And if it's of size 2, then entropy of A equals to 1 by the normalization axiom. If it's larger, we know that the entropy can only be larger by what we proved in the first part. So this is true when A equals to 1. If A equals to 1, by previous lemma, we know that the entropy of X equals to 0. And we know B is at least 2. So the entropy of Y is at least 1 by the first part that we proved and normalization. Okay. We may then suppose A is of size at least 2. So entropy of X is uniformly distributed over a set of size at least 2. Its entropy is at least as large as a random variable distributed uniformly over a set of size 2, which has entropy 1 by normalization. So this entropy of X is at least 1 by normalization. Okay. What we need to prove is now B is strictly bigger than A. We need to prove this. Take independent copies of X and Y. Let Xi, Yi be independent copies of X and Y respectively. All right. Since A is strictly less than B, we can find a sufficiently large constant n so that the size of A to the power n is at most the size of B to the power n minus 1. This is possible since B over A is strictly bigger than 1. Okay. Then what do we know? We know, let's look at this joint entropy of x1 to xn, n independent copies of X, and the entropy of m minus 1 independent copies of Y. All right. What do we know about this? Well, what is this random variable distributed? It's distributed uniformly random over a set of this size, right? Because each xi is uniform random over a set of size A. And these is a random variable distributed uniformly random over a set of size b to the n minus 1. Okay. So what do we know about these two? We know this by the first part. When you have two random variable uniform random distribute over two different sets, one is at most the size of the other, entropy satisfies this inequality. On the other hand, previously we proved that in joining information of independent random variables equals to the sum of them. So this equals to n times h of x, whereas here this is n minus 1 times h of y. Okay, then we are done. H of x is strictly less than h of y by this. Okay. Much time we have? We have 15 minutes. Okay, so now there's another here's another important property called non-negativity. We already mentioned that entropy assigns non-negative real values to a random variable. That's we sort of take it for granted. We mentioned that we're going to start everything just from pure axioms, those 6 axioms. We can actually derive from those 6 axioms that entropy assigns non-negative values to random variables. So let x be a random variable on some finite set A, then h of x is non-negative, it's entropy. Well, to prove this, it's a little bit tricky. We have to define some. We have to introduce a construction. So here, let's sidetrack a little bit. For a random variable taking rational probabilities on atoms, it is helpful to link it to a uniform distribution. We can link it to a uniform distribution as follows. So here's the construction. So suppose x is a random variable on A, where the probability that x equals to A it's a real, let's say it takes rational value on atoms. So we can normalize it so that it takes value MA or M sub A over N for the same N. And M sub A is an integer where for some natural number MA. So what is x? This is just a random variable taking rational probability on atoms. How we can link it to a uniform distribution? Well, let's now take a random variable u, uniformly random, distributed over a set of size n, the same as this denominator. Now we're going to partition n into A parts, where each part VA equals to MA. We just take an arbitrary partition. Remember, if you sum over all A in A, this equals to 1. So the sum over MA equals to N. We can just take an arbitrary partition, cut it into pieces. Each piece corresponds to the probability that X takes value little a. Now we're going to define a random variable X prime on A as follows. This is a random variable that depends on U, basically. So X prime equals to A if U lies in VA, when U is uniformly distributed over N. You will see that X and X prime, they are identically distributed. X prime is just a different way of sampling X. So X and X prime, they are identically distributed. Okay. In particular, by invariance, they have the same entropy. Another thing is, by invariance, the join information entropy they carry is the same as just U itself carries. Simply because if you know U already, you know exactly what is X prime. Okay? So the information that U gives you is the same as their join information by invariance. Okay. Another property is that conditioning on X prime equals to A. If we already know X prime equals to A, we know that U must lie in VA. Condition on this, and knowing that U is uniformly distributed over N, we know that U is now uniformly distributed over VA. Let me write it like this. The random variable U conditioned on X prime, equal to A, this itself is a random variable, is uniformly distributed over VA. Do I need to say more? Okay. Now, seeing this connection, which is a simple connection, we can prove the non-negativity. Let's prove this. Okay. Proof of non-negativity. What we do is we first assume X takes rational values over A. If it's not rational, you can use continuity axiom to approximate the probability by rational ones. All right. By continuity axiom, we may assume X takes rational takes values in A with rational probability. Now, let U be uniformly distributed over N and X prime defined as above in this construction. So X and X prime, they are identically distributed, and the joint entropy of U and X prime equal to H of U. Okay. Now, let's use additivity. Additivity says the joint entropy of these two equals to H of X prime plus H of U X prime. Okay. We then get that we have H of X equals to H of X prime. They are the same, identically distributed, but H of X prime equals to, by the above additivity, their joint entropy minus the conditional entropy. Okay. But what is the joint entropy? It's the same as entropy of U. So equals to H of U minus H of U conditional X prime. So if we can prove that this is bigger than 0, we are done. Right? We want to prove H of X is at least 0. In other words, we want to prove this is at most this guy. Need to show the conditional entropy is at most the entropy itself. Later, we will prove this in the more general form, but in this particular case, let's prove it in this scenario, which is sort of intuitive, right? The information you get from U, that's the right-hand side. Left-hand side is the additional information you get from U after knowing X prime. So if you already know a little bit something, the additional information can only be lower, less information. Okay. So how do we prove this? Well, recall, for each A in A, if we know X prime equals to A, then this random variable, conditional random variable, is uniformly distributed over VA. This is one of the properties we mentioned above, right? Then, and we know that U is uniformly distributed over N. Remember one of the lemma we proved, if you have two random variables uniformly distributed on two different sets, where one set is smaller than the other, then the entropy of one is at most the entropy of another. So we have, by previous lemma, this conditional entropy is at most the conditional entropy of U. Okay. Remember this lemma. Let me show you where it is. It's this one, monotonicity. This is monotonicity. You have A, you should think of this as random variable distributed over a set, which is smaller than the other set on which the other random variable is uniformly distributed. So monotonicity implies this. And that's true for all little a. Since this is true for all little a, we can drop this conditioning. So this implies H of U conditional X prime equals to, by definition, the probability that X prime equals to A, the conditional entropy conditional X prime equal to A, which is at most by the above inequality, sum of A in A okay. But then this is H of U. We are done. All right. I think I'll stop here for the first lecture. So this first day, let me summarize what we proved. We talk about this definition of entropy. And we saw this application on estimating the volume of Hamming ball on the use of entropy. And then we switched to talk about entropy in the axiomatic approach. And the axioms, we have 6 axioms. I will not repeat all of them. And there's some basic property of it. Independence properties. And non-negativity that we just proved at the end. Monotonicity. What else? I think that's what we covered so far. Okay. Any question? So the first 2 lectures will be sort of theory building. We're gonna go using the axioms to derive all sort of properties of this entropy notion. And then after the first 2 lectures, we're gonna start seeing some applications, how we can use these properties to prove various statements in combinatorics. Okay. Thanks for listening. I'll see you guys on Thursday.